Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's an honor to introduce Ingrid Zuckerman, who's visiting us today from Melbourne, or Melbourne, as they say, I guess, if I pronounce it correctly. I was there last Christmas, visiting Ingrid there. Ingrid was actually most famous as a visiting researcher at Microsoft Research in 1999? 2000. The 1999-2000 academic year. And she's a professor in computer science at Monash University. She did her bachelor's and master's work in operations research at Technion, and did her PhD research at UCLA. Famously, again, is one of the early grad students of Judea-Pearl, the first Judea-Pearl grad student working in Bayesnets and uncertainty, I think, right? One of the early ones.
No, the only one working in natural language, actually.
With uncertainty. Oh, certainly that's the case. Yeah. That's probably still the case until this day, almost, right?
But yeah, I was the first person to actually do Bayesian propagation by hand ever on the planet.
It's nice to have an interactive introduction, isn't it? You can check my years and my details here. We're doing a dialogue-based introduction, thematically placed. Anyway, her interest areas are discourse planning, interpretation, plan recognition, and dialogue. So, Ingrid.
Thanks. Yeah, sorry to interrupt. It was all right?
That was planned.
Okay, what I'll be talking about today is a spoken dialogue system we're developing for a robot. And, well, about the motivations for the way we are developing the system and where we are so far. So, the name of the system is DORIS, and it actually has an acronym, Dialogue-Oriented Roaming Interactive System. And DORIS is a dialogue module for a robotic agent in a home. And eventually it will combine spoken and visual information. And actually we used to have this Wakamaru robot, but Mitsubishi Heavy Industries took it back. But I still like the picture. So this is the sort of thing that we are aiming for. The user might say, can you get my mug? We are fixated with mugs. And Doris might say something like, I don't know which is your mug, but I can see a blue mug. And the user might say, my mug is the one on the table. And if Doris can do that, we will be very proud of Doris. Because this type of dialogue highlights a number of issues. First of all, it highlights the fact that Doris needs to be able to identify objects in the world. And it also needs to, is this thing? Yeah. It also needs to be able to understand from this that the user's mug is not the blue mug, which is actually a very tall order. So if Doris can do all that, we'll be very happy. But at the moment, we are on our way. So what I'll be talking about is I'll be motivating our design decisions. Then I will be talking about our interpretation of spoken language. And yes, what I should mention is at the moment, we are not doing any dialogue as such. All we are doing is interpreting what people are saying. We are getting to dialogue. Then I will be talking about how we estimate the probability of an interpretation of a person's utterance. And then how we evaluated that part of the system. Now, what you see in light blue is, if time permits, I'll be talking about our more recent work about an interpretation of a sequence of utterances. Because people normally don't express themselves in one very smooth sentence, but they're actually quite segmented. And then conclusion and future work. So first of all, the motivation. So what are the things that we want Doris to do? We want DORIS to make decisions on the basis of the result of the interpretation process, and these decisions are both dialogue actions and physical actions. Now, what are the results of the interpretation process? They are not just what we understand one utterance to be, but also how many alternatives there were, how close they were to the best interpretation, what were the differences between these alternatives, just one word that was different, or was the whole thing different? And the decisions about what to do depend on all these aspects of an interpretation. We also would like DORIS to modify decisions on the fly if it receives new information. So it has heard an utterance, made some type of decision, and then a new utterance comes. And also we would like DORIS to recover from flawed or partial interpretations. So it got it wrong, and then there is new information, and how do we recover? So in order to support all this, we decided that we need two things. We need to be able to maintain multiple interpretations, and we need to be able to rank them. So you need multiple interpretations, so you can do all that. First of all, you need to know how close they were to each other, what were the differences, and so on. If you want to change your mind, you want to know what to change your mind to. And if you want to recover, again, you want to have your alternatives in hand. And of course, to know where you stand, you need to be able to rank all these interpretations. So these are the two things we want DORIS to be able to do. And yes, Scusi is the speech interpretation module of DORIS. Yeah, no idea why we call it Scusi anymore, but that's how it stays. So what I will be focusing on from now on is about Scusi, and Scusi has to do these two things: maintain multiple interpretations and apply a ranking process. And to maintain multiple interpretations, what we have is a multi-stage interpretation mechanism, and each stage maintains multiple options. And so that this thing doesn't explode for us, we have an anytime algorithm to do that. So our algorithm basically keeps track of all these multiple options until time runs out, or in our case, until we have generated a particular number of alternatives, and then proceeds to pick the top few alternatives. And the ranking process is done through a mechanism that estimates the probability that a particular interpretation matches the speaker's intentions. So these are the two things that I'm going to talk about: our algorithm and the mechanism for estimating probability. So the stages of the interpretation process is, so far we are using a pipeline process that is quite normal. We have a speech recognizer that produces text, syntactic parsing that produces a parse tree, semantic interpretation that produces a concept graph that is based on SOAS conceptual structures. Now, the idea for this, we know that in spoken dialogue systems, a lot of people use semantic parsing, but the idea for this particular structure was that we want to get to the situational context as late as possible so that we don't have to redo a lot of the initial work. And in fact, there is one piece of research that we're fond of citing by Knight et al., who say that if you have a situation where people will say unexpected things or are not familiar with the system, you are better off with this type of model rather than semantic parsing. So the first stage is speech recognition, and yes, we are using Microsoft. It works very well. And in fact, we are using an old Microsoft. Tim Peck assures me that the new one is even better. So the Microsoft API produces a range of interpretations, and they are all scored. And we transform the scores into probabilities just using a linear mapping function, nothing too fancy.
What do you mean by that?
Oh, the API produces numbers, and then you normalize and you turn them into numbers between 0 and 1.
I see.
Yeah.
Basically, you're using those numbers as probabilities directly.
Yeah. But yeah, exactly. Then syntactic parsing, we use Charniak's parser, and that parser returns any number of interpretations, and then you get something that looks like that. And in the semantic interpretation, as I said, it relies on concept graphs, which is structured by SOA, that represent entities and relationships between them. And we have broken down the process into 2 stages, uninstantiated concept graphs and instantiated concept graphs. So uninstantiated are basically pure semantics, and instantiated are contextualized in the environment. And as I said before, the reason, again, even for this breakup is that we want to leave the domain instantiation for as late as possible. So an uninstantiated concept graph, all it does is it links, it basically it is a different representation of a parse tree. And it is produced directly from a parse tree. However, one uninstantiated concept graph, or UCG, can have multiple parent parse trees if they mean similar things. For example, you could have a parse tree like the blue mug, and sometimes it's a direct adjective, and sometimes it is parsed as an adjectival phrase. And both of them will lead to the same UCG. And as I said one more time, domain independent, so we are not looking at the domain just yet. So for example, here is find the blue mug in the kitchen for Susan. And what we have is a UCG that has all the right bits directly generated from the parse tree. And the only thing of note is that attributes of the nouns are included in the boxes for the nouns. So if we say the blue mug, the big mug, a mug, all those things are included in the box. They don't have a special node associated with them. The instantiated concept graphs pertain to the domain. So now that we have an uninstantiate, we want to know what things in the domain actually can match this situation. So here we have, again, the blue mug. And now we have a particular instantiation, which means a particular interpretation of find, like we have different kinds of find. You can find somebody's office, which means you just locate it, whereas you can find somebody's mug, which means locate and retrieve, and so on and so forth. And, well, all the things have numbers, even though patient, we have only got one kind of patient and one kind of beneficiary. We have 3 kinds of cups, 2 Susans, 1 kitchen, and so on. So this is a particular instance that we have generated from what we have said. And of course, all the cups and mugs in our domain could be possible instances. And all the Susans could be possible instances.
So here you generate by just going across all options, and is it all possible combinations?
Almost. Conceptually, it is all possible combinations. In practice, you'll see in about 5 minutes that we reduce the search. But conceptually, yes, it's all. OK, so how do we search for an interpretation? We have, this would be the result of a search so far. So we have a speech wave, we have a bunch of texts. Each text can have a bunch of parse trees. Each parse tree can generate 1 UCG. But you see, for example, the UCG over there, 22, can come from 2 different parse trees. And 2 UCGs can also produce an ICG. So this is the search structure that we generate. And the algorithm works like this. While there is time, select a level to expand, while preferring low levels. Basically, we want a beeline to a solution. We don't want to meander around the top and not have an answer. And this is done like the preference for low levels is done probabilistically. Basically, each level has a probability, and the lower levels have a higher probability of being selected. Select an item which prefers promising candidates. And what is a promising candidate? A promising candidate is a good parent. So how do we decide who is a good parent? This is like Darwinian. Okay, if a candidate has not generated any children, but it has a good probability coming from above, he's allowed to procreate. Once you have generated a child, you are only allowed to procreate so long as the probability of your children is good. Once you have generated a bad child, you can no longer procreate. That's it, you're banned. So that's a promising candidate. And once you expand an item, you generate only one child at a time. So you don't produce, even though the parser does generate its 50 parse trees, we pick them out one at a time. And likewise with text, we pick them out one at a time. I mean, the fact that the speech recognizer and the parser generate all the options at once, it's an artifact of those products. But if this is truly any time, we want to pick them one at a time.
So you'll explain the scores like that you give to each child later? Or?
Yes, it's all coming. Here. Yeah, so how do we estimate the probability of an interpretation? This is the complete development of this formula is by doing the base voodoo that one does, so chain rule, conditional probability. So this is the bottom line. Now the fancy C's pertain to context. So what does this formula tell us? It tells us the probability of an interpretation I given a speech wave W and some context is, let's leave the summation aside for the moment, the probability of a text given the speech wave, the parse tree given the text, the UCG given the parse tree, and the ICG given the UCG and the context. And it works out with the probabilities. It works out very beautifully. Why do you need a summation? Because everybody can have multiple parents. The text can be a parent. The same parse tree can have multiple text parents. The same UCG can have multiple parse tree parents, and so on. And the ICG can have multiple UCG parents. So that is the formula. And now where do we get that stuff? Okay, from speech wave to text, from the ASR. From text to parse tree, from the parse tree. This is a 1 because it's algorithmic. And this is the hard part. So this is what we're going to talk about now.
How complex are utterances in this domain typically? I mean, do you actually need all this machinery of the parsers say, or could you achieve a similar result if there's just a few arguments with a template? Okay, the thing is, yeah, we have done trials with people and they meander all over the place. And in fact, you're going to see it at the end. And this is why this is not a command and control situation. Yes, you could train people to say, tea, Earl Grey, hot. Yeah. For Star Trek geeks, that means something. For the rest, never mind. But most people actually meander all over the place, and you are telling them, pretend you're talking to a robot. So even with all this machinery, you will see later, we can process only a fraction of what we are being told. And there is another piece of research actually from the last interspeech that the older people are, the more they meander in their discourse. So yeah, if this is going to assist anybody of age. Okay, so now how do we calculate this probability? So we have 3 different sections, and it all become clear. The first section is an intrinsic match probability between a node in the ICG and the corresponding node in its parent UCG. So if you have a match node for node, like we saw before,
You want the probability that the person uttered a particular description when they intended a particular object in the domain. This is the first section here. The second section is a structural probability. It's the probability, I mean, in principle, we would like to calculate the probability of a complete structure, but we don't have that. So what we use is we use trigrams, which have the structural probability to represent the structural probability of an ICG, and this is the probability of a node given its parent and its grandparent. And we'll see an example in a moment. And finally, we have the probability of a node. This is an instantiated node, given the context. And at the moment, we are not doing anything with this other than our knowledge base of nodes. In the future, we want to include visual salience and discourse salience. So this is where you would put all of that information. But at the moment, all we have is, do we know about this thing or not? Okay, so now we are going to go into how we calculate, how we make these calculations. But before that, we have some simplifying assumptions. The robot is co-present with the user and all possible reference, and it has an unobstructed view. And each object is uniquely identifiable. Now, the first two assumptions we make because at the moment we only want the robot to make linguistic decisions. We don't want it to make a decision that says, there is nothing really good in this room, maybe I should go look elsewhere. Or maybe I should move a little bit to get a better look. I mean, these are decisions that will have to be made in the future, but at the moment we don't want to deal with this. So we have co-presence and full view. Unique identification, that has to be removed if you are going to deal with a vision system, because realistic vision systems don't have unique identification. And in fact, we have a version of the system that we call visual DORIS that has a simulation of a vision system. Okay, so now we're going to go for the features that we are using in our comparison. So intrinsic matches, which is what is the probability that we set a particular description when meaning a particular node, pertain to lexical item, color, and size. And yes, we can extend it to texture and shape and other things, but once you figure out lexical item, color, and size, you don't get brownie points for extra things. And structural probabilities pertain to ownership and location. So these pertain to the relationships between concepts. And we need to distinguish between intrinsic and structural, because intrinsic are features of a thing itself. So if I want the blue mug, this is it. The mug is to be blue. But if I want the mug on the table, I have to consider all the mugs I know about and all the tables. So I have to consider these trigrams. Okay, so this partially answered Dan's question, are we doing everybody against everybody when we are building these structures? No, we want to find good candidate objects. So, and what is a candidate object? A candidate object would be also something composite, like the mug on the table. So to do that, we do it in two stages. At the first stage, we make a list of candidate objects for each UCG concept U. For each mug, each table, each concept that was mentioned, we make a list of candidates. And we estimate the match probabilities of those candidates. So if I ask for a blue mug, I look at all the cups and mugs and dishes, and the ones that are blue win. And then we rank these objects in descending order. Next, we make mini ICGs of candidate composite objects. So now we want to disambiguate referring expressions. And the mini ICG is an ICG just for a referring expression, no verb. So the mug on the table, near the lamp, in the corner. We want to find candidates for that. So we combine individual candidates into composite objects, and we estimate their structural probabilities and rank those. So we retain, at the end of this game, we retain candidates for composite objects. And now we can put them together in a larger utterance. So in principle, it's everybody against everybody, but in practice, it's only different composite objects against other composite objects. Okay. So what is the probability of a match? So now we are drilling down to intrinsic probabilities. So what's the probability of a match between a UCG node and a candidate instantiated concept? So the probability that we meant K and we said U. And as I said, at the moment, we are only doing lexical item, color, and size. So if we assume some feature independence, we can break it up like this. And yes, color is not 100% kosher, because color also depends on lexical item. Red hair and a red mug is totally different reds. But we're looking for household objects. So we're pretending color only depends. So the probability that you call the thing with a particular name, that you indicate that it's color, and that you indicate that it's size. Now, size does depend on what you asked for. A small elephant and a small mug is two different sizes. So, and then again, we have heuristics to estimate each probability, and we do a linear mapping. We have heuristics to estimate scores, and we do a linear mapping to estimate probabilities. So let's have a look how we estimate the scores. For lexical item, we used one of the many WordNet similarity metrics, and we picked Leacock and Chodorow's because it gave the best result. And it didn't crash. And
after a massive search through all possible methods.
What's his name? Pedersen. He has a list of like 6 different methods. And we just tried them out, and this one was the most sensible. So it returns a similarity score between the name that you used and the name that you might call a particular object. So a mug is called a mug, and then you might call it a cup, a mug, a dish, etc. And it returns a similarity score, and S max is the maximum possible similarity.
How did they build that model?
Leacock and Chodorow, WordNet distance. Distance on the tree and maximum distance. But there are all sorts now.
But mostly using WordNet, not other corpus.
We didn't use the corpus-based one. Just that one seems to work. And color, our model for color similarity is based on the CIE model that the authors claim that it's psychologically grounded. So we use the Euclidean distance, that's ED, between the color that was stated and the actual color of the object based on these LAB coordinates. And LAB stands for brightness, some number in the green-red spectrum, and some number in the blue-yellow spectrum. And for size, this is actually a fairly new size function with a different one. We have heuristics that map sizes into a requested size into 2 states, large or small. And then we estimate the probability that an object could be designated large or designated small. And this probability depends on the average, mu lex is the average size of objects of the type, and sigma lex, the standard deviation for objects of the type. Where did we get these numbers? The IKEA catalog and Amazon. So if you want a bed or a mug or whatever, we just took a lot of mugs, average sizes. And then you have the probability that something could be called large or something could be called small. So now that we have all these probabilities, how do we combine them? According to Dale and Reiter and Wyatt and our own survey, people use the type most often, absolute adjective second, and relative adjective third. So color is an absolute adjective, and size a relative adjective. So we had a weighting scheme. We raised each probability to a particular power, and we did experiments to find out which numbers give the best result, and that's what we found. And yes, you can use machine learning to do that, but we didn't. We just tried a few things until we got something that we liked. Okay, so how does this whole thing work? As I said, we're fixated with mugs. And
it sounds like you can do whole studies on each of these components.
Yes.
Users and
yes.
write paper per component. You're finding lots of graphs and trade-offs and optimizations.
We did a few, but yeah, the thing is there is always a trade-off between moving on and dwelling on a particular issue, and we move on. But yeah, if I had unlimited manpower, I would dwell. So say the large black mug, and we want to know the probability that cup 1 could be called the large black mug, or mug 1, or mug 2. And then this is what we get. We get, for cup 1, on Lexical, we're doing medium, because we said mug, and the best name for it is a cup. Color is good. Size, no, it's kind of small. Mug 1 is doing bad on color, and mug 2 is doing pretty good. So in this case, mug 2 is the winner. Yeah, it's a clear winner. But if we don't have a winner, the question is, what would we do? And this is where we get into the next part of the project that we haven't started, is it worth asking? I mean, how crucial is it to this person to have a large black mug? So this is the next part of the project. Okay, so now we finish with our intrinsic probabilities, and we move to the structural one.
And you meant asking in real time, or asking as part of training? So.
No, asking in real time, like a person, get me the large black mug. Doris goes to the kitchen. Well, should I go back and ask?
If the black mug is filled with coffee and the other mug is empty in the cupboard, it's a big difference. So
depends if they want coffee or water.
But I'm saying, but which one?
Yeah.
It's not just mug; it's the actual experience and location and so on. So it can be definitely worth asking sometimes if you don't know.
Yeah. Oh, absolutely.
I'm surprised you actually couched it as what,
No, I say, like, sometimes you want to ask and sometimes you don't, but it's a non-trivial decision whether to ask or not.
Right.
Okay, ownership, very simple heuristic function. Like, this is what you would have in your tree, whether, Susan's mug. So you want to know the probability that of this particular bit of the structure, whether Susan owns this mug, and it's 0 if you know for sure that Susan doesn't, 1 if Susan does, and some alpha.
And here's another good application for our home robot of the future. It'll be, you're at a party, get rid of all your little, this is my wine glass dangling thing, and have the robots track it. Where's my mug? That's your mug. So you have to watch
your RFID tag, you have all your...
Just a little camera up in the ceiling, they can find your mug for you. Or your glass, you don't have to sort of wash one, get a new one, So it'll save on all those little cutesy little dangling jewelry you can put on your mugs.
Yep. So that is a very simple heuristic. Our positional stuff is, well, I think it's kind of cool. Again, a few assumptions. All objects are rigid. So that means that they can be represented by a box. And they have 3 dimensions, length, width, and height. So if somebody wants their pants, we assume their pants are not just draped all over the place, but they're in a box. So we have heuristic functions for locations, such as on, under, and above. And for that, what we do is, if the directional semantics is satisfied, then the probability of a particular location is proportional to the shared surface area. And I'll show an example in a moment. We can have in that is proportional to shared volume, and near that is based on Kelleher's gravitational attraction. So just to clarify, how does this work? If I want the book on the table, directional semantics means that the z coordinate is actually correct. The z of the book is the table plus the height, the z of the table plus its height. Now that I got the directional, then I'm going for shared surface area, which means the probability that the table is on the book is the shared area, sorry, that the book is on the table. It's the shared area between the table and the book and the minimum between the both. Because you could have a book overhanging slightly a table and it's still, the book is still on the table. So this is for on, and now that we have seen the example for on, we can go back to in. So that's shared volume. And near is basically, the idea is that near objects, well, the nearer an object is, it's better, but the measure of nearness for bigger objects is more slack than for smaller objects. The pen next to the laptop is one thing, the sofa next to the table doesn't have to be like this. Okay, so now we start our evaluation of this part of the project, and we had a few experiments. We had more, but I'm talking about these. So the first experiment was referring expressions only with intrinsic features. The second was full referring expressions, intrinsic and structural. And the third was complete utterances. In all experiments, we generated at most 300 sub-interpretations, so everything, text, parse, trees, UCGs, ICGs, we set it to 300 as a limit. And one speaker spoke all the utterances, and that was Enes. And yes, people complain about this. Why don't we have multiple speakers? Because you have to train the API. You guys know that. So
It'd be interesting to see how things degrade, though, without training, for example.
well, somebody has to train it.
Well, I mean, you can just use. I mean, you could just use the defaults.
The defaults are American.
We'll fly Dan out. You know?
Yeah, it didn't work because that's why poor Enes had to read Moby Dick to it for 2 days.
I do think, like Eric, I think that's a good point. Like, it's especially like it'd be interesting to see if you vary the quality of the recognition. You know how because you're combining here a number of factors, right? There's the uncertainties that come from the recognition, and then from the parsing and the understanding.
Yeah.
You know,
And to see it,
I
as you turn
remember
those
some
knobs.
results from a long time ago on exactly this question that involved asking, this is many years ago, and I don't remember the citation at all, but getting people to chat with in a Wizard of Oz setup with a dialogue agent that had varied synthesis quality. So they were actually talking to a human behind the curtain, but the synthesis quality varied from human quality to really tinny, cheesy, and there were huge differences in how people talked to the person behind the curtain. And, you know, when it was tinny, poor quality, robotic sounding, they foreshortened things. They used
All right.
fewer adjectives, much simpler syntax, and when it was human, they just spewed out.
This is the listening side, though, right? I'm talking about.
Yeah, that's true. So
I mean, because one of my big concerns is, or I think it's so far fabulous and very interesting, but the concern is we're seeing intelligence and the glimmer of hope when it comes to very carefully crafted, very carefully spoken, good recognitions more generally. And what happens when it's more, there's some noise in the recognitions and people talk in really out of band ways? Will the various safety nets and expansions you have from like coordinate and similarities and so on, is the structure from the physical environment enough to collapse it down at that point? And
That is...
big question, I think.
Oh, yes, totally. I mean, at the moment, we are poor over there. So Microsoft API was free, and we had to train it, so Enes was it. Because Enes' accent in English is better than mine. He's from Bosnia, actually, so...
No, he's from Boston?
Bosnia.
Oh, Bosnia.
Yeah.
Boston.
No. No.
Boston is a bit different than Chicago, isn't it?
No, but I totally agree that we should have multiple speakers. What we did do, though, is people did generate the utterances, and NS just read them out. It wasn't all of NS's utterances.
I see.
Right.
Okay.
No, NS was the reader.
Okay.
Yes. No, a lot of the utterances belong to other people.
How are they generated by the other people? Like what
It
process?
all will come.
So he
Oh.
did simultaneous translation into Bosnian accent that
Yeah.
he then recognized.
Yeah. Okay, so this is our first experiment. Yes, this is IKEA. And IKEA in Australia. And we had 6 words, and we asked 8 people to identify labeled objects. And the worlds were the pen world, the mug world, the furniture world, and so on. And we would say, like, describe D, or describe L. And they had to generate a description. So there were, in total, 57 possible referents. And people generated 178 descriptions, out of which we could use only 75 because people do not follow instructions. We said our system can do, at the moment, lexical item, color, and size. Nothing else. They asked for the rectangular tray. Okay, so...
Pause there for a second.
Right.
Yeah.
In reality, that's always going to happen. Our systems will always be incomplete. And what's your sense for if you were given $1 million by the
Netflix.
But no, we'll say $1 million from government, Australia, to do general research, and you wanted to fix that problem of assuming incompleteness. How would you solve that problem?
Well, I would go for the numbers. Like, assuming that I get such a corpus study, you say, okay, so people talk about, well, there are 2 issues. One, what they talk about, and 2, what a robot can recognize. Because people spoke about texture. There is no way on earth a robot can recognize the velvet couch as opposed to the woolen couch.
Ingrid, what about 3? A robot that understands it probably doesn't know everything it's going to hear.
That's fine. That we can deal. I mean, well, we can't, but we... Well, no, okay, so the thing is, the first order of business would be do the corpus study. So things like shapes. And so I would incorporate the other things that we're not incorporating because we're not getting brownie points for incorporating them. After that has been done, the rest of the stuff is in the vocabulary. It's just not stuff we can deal with. So then you say, okay, you said woolen. I'm sorry, I cannot identify wool. And
Or go beyond these other constraints.
Exactly. So it is doable.
Maybe learn what one means later.
But still, I mean, visually, the robot would have to go up and touch it and do a tactile identification of wool as opposed to velvet. I think people will have to get used to asking Doris for things. I mean, once you tell it, it has not tactile sense, and it can only see, then I hope people will become sensible.
Just popped in. I was trying to say Canberra. $1 million from Canberra.
Canberra is not giving anybody $1 million. Yeah. Canberra just gave every Australian $900 to spend on plasma screens, but we can talk about that later. Okay, so in any event, this was the experiment, and we ended up using only 75. There were some duplicates. But yeah, people were a bit naughty that way. So these were our results. ASR error is 26%, so it's not like, maybe the next version will do better. And gold reference in the top 1 out of the 75, we got 49. But in the top 3, we got 87%. So we are actually overcoming ASR error for top 3.
What does gold rest mean?
We knew what was the gold reference, like what we want. The gold is the correct one. So we said, like, we spotted the correct one in 87% of the cases for top 3. We didn't find one. Which one was the one we didn't find? Oh, poof. Doris didn't know poof. And, oh yeah, and also the API had trouble with Australianisms like ramekin and biro. Not a chance of getting it to recognize that.
What does it mean?
Ramekin is a cooking, it's a little cooking dish, and a biro is a pen.
You say it like it's common.
In Australia it is, that's the thing, we're not used to it.
Ramekin, isn't that the thing that they do the creme brulee?
Yes,
Yeah.
there you go.
We have those here
I'm
too.
showing my, my wife would be upset to hear my conversation right now.
Well, so we didn't find the proof, and the average rank was 0.82. So what is the rank? Rank 0 is best. A poof is a little round chair, like a... Do we have a poof here?
Is it Europe also?
This is a poof. H. H is a poof.
The Ottoman.
Well, some people call it a poof.
It's a little
Oh,
round,
really?
Yeah.
Yeah.
J could also be a poof, no?
Now, is that used in here also? I just don't know about it.
I've heard it.
There you go. You've been illuminated regarding furnishings.
For homosexual.
Is poof?
Yeah.
Yeah, but different accent.
No.
No?
Not in the UK.
It's one syllable.
No. In Australia, it's 2 syllables actually too.
Poof?
No, poofter. They call
Oh.
it. Right. Okay. We proceed. They're recording this.
It's okay. It's PG-13. Here.
Yeah.
So gold references, so those are the actual ultimate like semantic representation that you generate, or I don't understand how to reconcile. SIR means
The ASR, it means that the top text returned by the ASR was not the correct one in 26% of the cases.
so it's sentence level.
Yes.
But you're only focusing on a small number of words in those sentences typically, right?
Well, actually, we use the entire vocabulary, whatever Charniak's parser has, whatever the ASR has. Yeah, we're not restricting.
No, but I mean, the bits that you're actually focusing on for the behavior of the robot, it's typically a small subset of, like a substring probably in a longer utterance. So much of it could go wrong, and as long as the...
Well, for this experiment, it was only referring expressions like the pink tray, the large blue tray. We'll get into the bigger expressions in a moment. So this was only referring expressions. And we got the 26% error rate. So in top 3, we're doing pretty good. And the rank means like your best rank is 0. So average rank is 0.82. Which means the best interpretation is either the top, the gold. Okay, the gold is either coming up top or second. So it's not bad. Okay, next experiment. We had a simulated house. This is a top view of our house. There are 5 people in the house, 54 objects distributed among 4 areas, and this is one area of the house. Now, these descriptions we generated, and I'll tell you why. Because I hope we are justified, but please complain. We did the same. Experiment 1, we also did with our own utterances. And the performance was the same. Whether we did it or other people did it, the system performed the same. So I figured, okay, whatever we're generating is not outrageous, and it's not particularly tailored to the system. So for this one, we can do our own. And we generated noun phrases comprising between 1 and 3 concepts. So things like a desk, the wardrobe under the fan, the mug near the book on the table, Paul's book. So these are the descriptions we generated, and now we compared against the baseline that was top interpretation for each stage. So just take the top. ASR error was higher now. We are sitting on 30% ASR error. And the baseline had, so taking the top, in 49% of the cases, the gold is top 1. Well, of course, if we only take the top 3, it's going to be the same. But not found is 46. For Scusi, we are generating, even the top 1 is already at 91%. So top 1 performance overcomes ASR error.
I'm not sure I understand what you mean when you say that overcomes ASR error.
Well, if you are taking top interpretation, like top ASR, top parse tree, top everything, and in 30% of the cases, your top ASR is wrong, then that's it. There's no way you're going to find the right thing.
Why not? Because the ASR could be wrong in well, I guess because of the nature of their sentences, but if the ASR number is sentence level, I could have the bits that you're using, like Bill was saying, could be all okay. Something else could be incorrect, and then I go and parse it, and I generate just using the top, and I still get the right result. Wouldn't that be possible?
How could you do that? Like if you said
So
whatever, like
let's say I want, so let's say
the mug near the book on the table,
Right, so
and the ASR got the mud near the book on the table.
So the ASR got mug near the book on the table without the initial the. Okay?
Right.
Count that as an ASR error.
Yes, I would count it as an error, but it also doesn't happen. You'll get an article there, but yes, I would count it as an error. Agreed.
And so then if I go with that through the whole chain, I might still recover the right thing.
Yes, that is true. And okay, we should check what kinds of errors we are getting. That is true. But the fact is, I mean, if you look at this, you get 46 not found.
Right.
So anyway, this is what you are getting. So whatever is the case, and the ICG is not taking into consideration articles and things like that. So it's really not finding the right thing. Whereas, yeah, Scusi is doing okay. We are happy with Scusi. And the last experiment is complete utterances, full requests. We picked out 100 utterances, and we actually ran an experiment. Okay, first I'll tell you what we have. So we have 100 utterances, 43 declarative, 57 imperative. We have 135 concepts in the knowledge base, objects and relations. And we actually collected a corpus from people. We asked people to interact with a robot, Michael was the robot, in 2 scenarios, tidy up and help me. Tidy up, they have to ask the robot to clean the house, and they have to say, pick up this, collect that, make the bed, etc. And help me, you have to be pretending to be disabled in some way, and you have to get the robot to do things for you. And people actually interacted with Michael in any way we could. So how do you call the thing that Microsoft does? The Microsoft chatting thing, MSN? Messenger, yeah, that. Messenger, Google Chat, whatever people could come up with. And they interacted with Michael. So it was typed interactions, and then NS read them. So our whole dialogue was 1,000 utterances, and we extracted 100 out of them. And this is our tidy up scenario. And I don't know how clear you can see it, but this house is very messy. Can you see the chair is out of place? There is a puddle near the door. There is a puddle in the kitchen. There are plates on the floor. Can you see them, or? Yeah, and these are sample utterances. Open the door to the cupboard in the lounge. The book is on the desk. And what we want them to achieve is this, where the house is all neat and tidy. So, and the help me scenario again, people, I forgot my pills, where did I put them, and so on and so forth. So in this experiment, ASR error is lower. I have no idea why the ASR error fluctuates so much. And ASR error is lower, and again, we have the baseline and Scusi. And out of 100 utterances, we have, again, we're beating the baseline. And the rank is pretty good. And we have only 7 not found as opposed to baseline 47 not found. So again, top 3 were doing better than ASR error. Oh, and here I collected some of the utterances that we had trouble with. Henry's little bowl needs a wash. So I suppose that would be an Australianism. That wouldn't be American English. Wash the shirt on the sofa in the basin, and it had trouble with inside the wooden box. Okay, so how are we going for time? Okay, I can do a fly-by-night of the interpreting a sequence of a sentence sequences. Bill was interested in that. This is like brand new stuff. We're still debugging it. So, okay, what happened is that people do not speak in these smooth sentences, but they actually speak in segmented form. And so what we want to do before we proceed to dialogue, we want to interpret a sentence sequence. And after that, we'll proceed to dialogue. So what we do is for each sentence, we generate UCGs. We determine their mode, declarative or imperative, and we determine coreference. Then we generate UCG sequences. So using the most promising UCGs for each sentences. So again, combinations. We generate mode sequences. We generate coreference sequences. And while there is time, we continue playing this game and selecting the best. So this might clarify this concept. So this is actually one of the utterances we collected. Go to the desk near the computer. The mug is on the desk near the phone. Fetch it for me. So then, after parsing, these experiments we did only with typed. We didn't even dare go for speech. Even with typed, we are having problems. So after parsing, you get the 2 prepositional attachment. The desk could be near the computer, or the going could be near the computer. Again, the mug is on the desk near the phone. The mug is near the phone, or the desk is near the phone. And fetch it for me. And again, prepositional attachment problems. So these are top 2 for every sentence. Top 2 parsing or structures. Now we can generate 2 UCG sequences. Then we have the modes, and the modes are pretty clear here: imperative, declarative, imperative. The second mode is very low probability in all cases here. And then we want to do coreference resolution. Like, which desk? Is it the self-reference desk or the desk in the previous utterance? Who is it, the mug or the desk? So we play this game and generate a lot of possibilities. And what's very pleasing is that we can actually continue our probabilistic calculations and extend them to multiple sentences. So if we continue with the same formalism, we actually get the probability of a UCG given the text, the mode given the parse tree and the text, and the coreference given all the parse trees. And the first component we get from a single sentence, like that's what we've done up to now. The second component, the mode, declarative or imperative, we get from a classifier based on the corpus, and the coreference we get on heuristics plus the corpus. And the heuristics we plan to replace with corpus-based information, but at the moment that's what we are using. So just quickly, coreference resolution, we can do pronouns, one anaphora, and just noun phrases, like the book. And because we don't have a lot of data, we do our Bayesian voodoo that we like to do. And we end up with this formula for coreference resolution. So this is the probability that referent I refers to, that referring expression I refers to J. Sorry. No, this is the probability of a particular referring expression J in sentence I. Sorry. And now we have the type of the referring expression, the probability of referring to a particular sentence, and the probability of referring to a particular noun phrase in that sentence. And yes, we had to break it up that way because we just don't have enough data to do all the noun phrases in all the sentences. So you break it up into referring to a previous sentence and referring to a noun phrase inside that sentence. Okay, so this is just the math very, very quickly. And now we can go for the evaluation, for which we need to do a lot more work. So we had an experiment where we asked people to pretend they've gone to a meeting and they've forgotten something, and Doris has to get something for them. And we got, again, and this was a web experiment, so people just typed stuff over the web. And we got 115 requests, and the vast majority had more than one sentence, and some people went to town and had up to 9 sentences. Now, this refers to what Bill said, that is, we actually had to make manual changes to even be able to process most of the sentences. Like things like, I need you to fetch. It's just fetch. It's not, and we don't do composite nouns at the moment. So coffee table was just table. And things like that. So we did all our systematic changes, and yeah, we have a plan, we have some hopes to apply machine learning techniques to translate from people English to Doris English. And this is an example of what people gave. Doris, I left my mug in my office and I want a coffee. Can you go to my office and get my mug? It is on top of the cabinet that is on the left side of my desk. This is actual input. And what we generated was this. This is what we can process. So, yes.
What are the bottlenecks? Like, what stops you from processing the entire thing?
Some things are just hacks, like Doris, please, things like that. We just didn't have time. That's all. I mean, those are little things. I left my mug in my office. This is narrative, right? It really means my mug is in my office, or I think my mug is in my office. But there is a lot of irrelevant narrative that what it indicates is a declarative sentence of where something is supposed to be. Right. So that is a problem. Then other things.
I guess my question is, like, if I was to try and take this as is and put it through the machinery that you have, why would it, like, what would you expect?
It doesn't do conjoined sentences. So I left my mug in my office and I want a coffee.
Like, who doesn't do it? The parser? The recognizer can do that, right?
We are getting between 20 and 30% error even on simple stuff. Like whether the recognizer can do it or not is a big if. Sure. The parser, I'm not sure. From parsing to UCG, definitely not.
I see.
We are not doing conjoined at the moment. So, I mean, these are all like, some of the things are pretty easy. If the parser behaves, you can break up conjoined sentences. Right? So some of the things, but a lot of it is really irrelevant narrative, or at the moment irrelevant. Like, yes, you might argue if it is, I want a coffee, maybe Doris should get the cup that has the coffee as opposed to the cup that doesn't have any coffee in it, for example. But if you're going bottom line, like translating from verbiage to command and control, all you want is, but this is what you really want. my mug is in my office, or
And this transformation, is this
manual.
automated or manual?
No, this is totally manual, but we have rules. Like we have somebody sitting there following we have a scribe following rules.
But these are not rules that could be easily implemented in a program.
Well, depends on what your program can do. Like,
Got it. Yeah.
yeah, some of them. Well, that's our plan is to apply machine learning techniques to see can you go from this type of structure to that type of structure, which is what
This
we
is sort of back to my question earlier. The syntactic machinery may actually hurt in a case like this, where you may be better off with a sort of Schenkian, templatic, word spotting approach. Just out of all this verbiage, you're looking for a few pretty straightforward types of information.
But the question is, you want to look for, I mean, if you do straight word spotting, then you'll find what you are looking for, and you may not find what is being said if they want something else.
Right, there'll be kind of a ROC curve in all the methods. I guess one comment is some alternate approach. So Tim Peck and I in Bayesian Receptionist version 1 had sort of a goal hierarchy. Admittedly, for a limited domain, kind of what receptionists do with a certain and other things that are outside of our model, but we actually did it. We as you might recall this work, natural language parse plus word spotting to use parts of speech and words that were kind of coded into a handcrafted Bayes net, and that has certain kind of characteristics. It means that's the kind of that's being recommended, that's being suggested here. That kind of it's not just spotting words, but spotting structure, linguistic structure as well, in a pretty tight context.
Yeah, that's the thing that, I mean, we were trying to stay away from context until now, but yeah, I prefer to do it, as I said, I prefer to do it at the end, but also for other reasons. Like at the moment we do this, right? We don't consider that the person wants their coffee. But if we want to do more sophisticated plan inference, actually recording that they want a coffee and knowing that will be important. It's just that at the moment we're pretending it's command and control. So, yeah, I take your point about the spotting, but I worry that it may be too restricted. So in any event, okay, here the evaluation we didn't do as well as we hoped, but at least we partially know why. So as I said, this was typed. There was no speech recognition. And for complete requests, we are at 51% in the top. And actually, it doesn't degrade. It's a pretty binary, the whole thing. Either we find it, and if we find it, we're doing pretty well. Like you see, the median rank is 0, and the 75th percentile rank is 1, if we find the right interpretation. But we don't find it in a lot of cases. Like in 31% of the cases, we don't find it at all. Now, we also did this evaluation for partials, which is just for UCGs inside an interpretation. Because for complete requests, you have to get all the sentences right. Whereas for UCGs, you have to get, well, you want to know how many you got right. So we do a little bit better, but still we need to do more work. Now, why aren't we doing, I mean, where did we fail? Okay, the first place where we failed is that we did not compose interpretations from several imperatives. Okay, one thing that I forgot to mention is that we're combining declaratives in this interpretation process. Where is it? Here, merge UCGs. I forgot, I kind of glossed over that one. Which means if you say my mug is on the table, it is blue. Then you get two merged interpretations. I have a blue mug on the table and I have a mug on the blue table, right? And we did all these mergers, but only for declaratives and for declaratives and imperatives. Initially, we thought that people would not add extra information into imperatives. We were wrong. People add extra information when they are giving more than one imperative sentence. So this actually accounts for 19 requests that we just didn't process properly. Anaphora resolution accounts for 6. Well, I mean, this is how it worked out, and we need probably better mechanisms for anaphora resolution. And PP attachment was also problematic. While we know that the mag near the laptop, on the mag on the table near the laptop, it's the mag that's near the laptop. Doris is not quite sure about that. So we have some ideas about to improve the PP attachment, but at the moment, this is problematic. So, yes?
But on a lot of these examples, I was noticing that when you were showing it, like these PP attachment, especially with near, you're still going to find the mug. In all settings.
That is a good point. Yes, that is a very good point, that we often actually find the correct object, but because our evaluation, like whether the mug near the laptop, on the table, whatever, you end up finding the right mug, but with the wrong structure. So at the moment, we're punishing ourselves for that structure.
Okay.
But yes, we end up finding yes, that is correct. So what have we done? Okay, we have our speech interpretation module that I've motivated. Keep track of sub-interpretations. And we have provided this probabilistic formalism that, well, to handle the uncertainty, but also what I like about it is that we are being able to extend it to multiple sentences. And we have an anytime search algorithm. And we are extending this formalism to sentence sequences. So where are we going next? Yes, we have to deal with ASR error, but also we have to do it for these multiple sentences. We hope to improve performance for multiple sentences to something reasonable, and then we'll go to ASR error. Extending grammatical capabilities, as I said, applying machine learning techniques is the direction I want to go to. We need additional dialogue acts, and then we'll move on to dialogue. And integrating with vision is if somebody gives us another robot. We can integrate with vision. Okay, that's it. Thanks.
Any questions? We've been pretty interactive the whole way through.
So I wonder if you might use like the environment to resolve some of these prepositional phrase attachments, like if you
yes.
if there's a mug next to the laptop,
Yes, that's exactly what we are planning. Actually, we are going to abandon the full pipeline. And yeah, next what we are going to do is for the UCGs, we're going to go down to the ICG level and see, okay, which ones actually exist. Yes.
It would also be interesting, I guess, I don't know, so you have there's a chain here of components, right? And each of them has uncertainties and failures and blind spots. It'd be interesting to see to which extent you could tease apart. Like I'm wondering, for instance, people have done all this work on just ASR re-ranking, right? If you were to take just your ASR results and apply some sort of like re-ranking technique that uses features that describe, some of these relationships that you're trying to capture. So just re-rank the ASR, and just pick the best hypothesis and parse it. Like how would that fare against, this approach where you're sort of keeping the uncertainties later in the chain, which I think is really interesting, right? So just that comparison, I think would be interesting to see. I don't know.
No, we tried it once actually. We used just vocabulary to re-rank, but to be honest, I don't remember what happened. Probably nothing much if I don't remember what happened.
And the other thing I think is like, so the ASR, I had a question about it. So you're saying like you're getting these 20%, 30% errors, and you're seeing those as high. And I'm kind of wondering, like in my head, they're actually kind of pretty good. especially if you're in a robot setting. I'm assuming like the experiments, like which you, like the ones you did with ASR, was it close talking microphone?
Oh yeah, totally. No.
So if you're with a robot in a home where the TV is going and the robot is like 5 feet away, right? You kind of have almost no chance. Like it's actually interesting, and I think these techniques have more space for improving things and for robustifying things when ASR is actually bad.
Yes, well, actually, an interesting point in one of the other experiments that we did is with visual DORIS, we had a simulated vision system and we cranked up the vision error up to 200%. So at the end, you could think a mug is an elephant. And the longer your description, like the mug on the table near the phone, the better the performance got. Because you had so many factors to disambiguate that even if you thought an elephant was a mug, at the end you didn't.
Right.
So
it'll be interesting, yeah, to see, like, I don't know if you get a chance in your future experiments to actually, I mean, it's hard to vary unless you do a simulated sort of model, like to vary the word error rate or the speech recognition accuracy. But what you can do is get a lot of people, and inherently some of them will have different error rates. And then you can just have that as a post factor sort of in your analysis and look at the correlations between, you know, when my error rate is low, how much do I improve?
yes, yeah, like you can, yes. And yeah, we can do the re-ranking thing again because I don't remember what happened. No, it was years ago, and for some reason we didn't pursue it. Half of me thinks is because we thought it was a bit of a cheat if you just add your vocabulary, like, you know, you saw we have up to 150 things in the knowledge base. So if you're just going to say, okay, I'm just playing with my own vocabulary and nothing else, it's a bit of a cheat. And also, people could be referring to things by their own vocabulary, like the chalice. Well, the chalice could still be a mug. Okay, it's a stretch, but you know, it's some type of vessel. So even though it's not part of your object, if people want to call something in that way and it's in some vocabulary, they're entitled to. But yeah, we should do a bit more with this.
Thanks very much.
Yeah.